Hey everybody, welcome back. Welcome to the kinetic versus potential energy section. Now there's a little bit of math involved with this. Don't freak out. It's going to be okay. But oh, I didn't want the arrow, the pen. There we go. But everything's going to be fine. Don't freak out. But the idea that roller coasters are very important in all this, and we're going to break this up into different sections. We're going to baby step through it. So don't worry about it. Here we go. A lot of this might be review to some of you, but here you go. First of all, some terms that we need to learn. The first is mechanical energy. Okay. Oh, I don't want that. I want a nice different color. Let's go. Oh, let's go blue this time. I don't know. Mechanical energy. So mechanical energy is exactly what you think it is. When you hear the word mechanical or a mechanism, all right, you should be thinking about things moving. Does anybody know what this is called? It's a medieval weapon. Does anybody know what it's called? It is a trebuchet, okay? And trebuchet did things where weight would drop, which caused this arm to fling, and this would start this, and it'd fling over, and they'd launch things over walls. But anyway, so mechanical energy, ME, is equal to KE plus PE. And KE is kinetic energy, and PE is potential energy. And actually, we could add another part on here, and that would be TE, which is thermal energy. And thermal energy, as we've talked about throughout the year, could be friction, it could be light. This usually is a negative quantity because it's usually the subtraction. It's where we lost energy. Okay? All right. So let's talk about the conservation of energy. Okay? So the conservation of energy comes into a big thing with this idea of the Rube Goldberg machine. Okay? And a Rube Goldberg machine is a machine that did very simple tasks, but through multiple steps. But what's the unintended consequences of it were that it showed great examples of the transportation of energy or transformation of energy. So we're going to start out with a Honda commercial that was filmed in Britain. And what's really cool is all of this is real. And well, we'll talk about it afterwards.
Isn't it nice when things just work?
And hopefully you got the joke there that worked because we were doing some force times distance moved across there. But the idea is from that first little sprocket that moved across the screen, this whole thing happened. Basically, the whole point of that was to close the trunk to basically show a car. So all those steps, the 600, I think it said 606 times they tried it, it didn't work. So all that effort and everything just to close the trunk of a car. That's what a Rube Goldberg was, a Rube Goldberg machine. But we're really just looking at the transfer of energy, just that little bit of energy rolling down there. All of that was transferred through to close that trunk of that car, which is kind of crazy. All right, this is a group called OK Go. You've actually watched a couple of their music videos already. What's really cool about this one is you can watch this one, and I cannot remember what college they went to, but they try to look at different ways to do music videos. So they do this one, and it's pretty cool. All from the start of just hitting this little car into a domino, you're going to see all of this stuff take place. So hopefully you see that. You can actually see behind here the images, and if you notice, they had paint on them already and stuff because they had to do multiple takes because again, depending if one of those little things, if one of those little energy transfer things didn't go off right, then you have to reset the entire thing. All right. So I heard it took like 300 or 400 or not 300 or 400, but like 40 to 30 to 40. Good gosh, I can't talk today. 30 to 40 times all the way through to get that exactly how they wanted it. So hopefully you understood that. Hopefully you think that's kind of cool. There's a lot of really cool Rube Goldberg machines out there, so feel free to search those up. Again, in the last video, we talked about what is a joule. A joule is a measurement of energy. It is really a Newton meter, but we just like to say joule, not joules like this, or hopefully not the ones you're using, but the joule is this guy right here. All right, so here are our equations. PE, potential energy, actually equals mass times gravity times height. Kinetic energy equals 1/2 mv velocity squared. Okay, and we'll talk about all that here as we go. But potential energy, the higher something is, the more potential energy it has. It has the potential to do more. On this, the more we swing the ball back, the more potential it has to do more damage or deliver more energy. If you've ever fired a bow, you know the farther you stretch the string back on a bow, okay, the more potential that that bow or that arrow has to going faster and harder. You've done this also on a swing. The higher you up on a swing, you know the more energy you have as you come through. So they are what we call inverses of each other. So down here at the bottom, when we first throw it on the bottom, we don't have any potential. We throw it, it has a lot of kinetic energy. It goes really, really fast. But then when it gets to the top, it actually for a split second will stop. At the split second it stops, it actually has zero kinetic energy because it's not moving. And then it has a maximum potential energy because it's at the top of its motion. Then as it begins to fall, it starts picking up kinetic energy until it goes right back where it started. It has maximum kinetic and zero potential. Here's a little graph. You've probably maybe seen this before. Potential energy. Notice the blue is maximum at the top. But as soon as it starts to move, we get some kinetic. But then at the bottom, when it's moving its fastest and it has no height per se, we say that it has zero potential. Here's two other graphs to look at it. Let's just look at the top one. I know the bottom one could be a little bit more interesting, but look at the top one. Notice as kinetic energy goes down, potential energy goes up. As potential energy goes up, kinetic energy goes down. Okay, but notice what stays the same. TME, total mechanical energy. That's really important as we move through this. Once we know the total energy, like right here, let's say it's 100, the total energy is 100. Now, as it changes, look, we get total energy of 100 kinetic and zero potential. Okay, it can bounce back and forth, but the total better always equal 100 in this case. I'm just making up these numbers, okay? But total mechanical energy never changes. All right, let's look at the bottom one. Same kind of principle, total mechanical energy. As they start to bounce, you see the transformation until what happens here? As soon as this guy or gal hits the unpacked snow, we say that negative work is happening, and all of a sudden the total mechanical energy starts to disappear, and it all changes into this work. Well, to be honest, it's not even really work per se. What this work really is here, this work is actually thermal energy. It's the friction. It's what's actually making this little skier slow down to a stop. And again, we're not really losing energy because you said, Mr. Tima, you said these two added together have to always equal this guy up here, and this can never go anywhere. Well, really, it's not that it goes anywhere, it's transforming into something else. So when this guy starts turning into thermal energy, if you notice, all the energy is being transferred into this thermal energy. All right, that's where we're going to stop for the day. We're going to do an online simulation lab, and then we'll come back with some really like 1 to 2 slide clips of these. Hopefully, we should be able to get through this pretty quickly, but make sure that you're asking questions. Again, it's hopefully you are finishing up on this chapter pretty strong. And as I always say, if you have questions, make sure you reach out. And until next time, Mr. Tima and Timatron out.